to our live webinar on analysis, optimization, and production of translucent nanoemulsions, hosted by Industrial Sonomechanics. My name is Eva Georgina, and I'm the Director of Marketing at Industrial Sonomechanics, and I'm today's webinar host. Today's presenters are Mr. Shlomo Leibtag, Research and Development Scientist at Industrial Sonomechanics, and we also have our guest speaker, Mr. Jack Saad, Associate Scientist from Micromeritics Instrument Corporation. Before we begin the presentation, I'd like to go over a few webinar details. We will be running a live Q&A session in the middle and at the end of the webinar. So we recommend that you don't wait until the end to submit your questions. To submit your questions to the presenters, please type them in the Q&A box located at the bottom of the Zoom screen. And as time allows, we will address as many questions as we can. Since this is a technical, scientific webinar, we will focus mostly on technical questions. But if you do have any other business-related questions or pricing inquiries, please submit them by visiting the Contact Us page from our website, sonomechanics.com. If any of your questions are left unanswered at the end of the webinar, we'll do our best to answer them offline after the event. And if you miss anything, we will also have a recording. Now, I would like to introduce our speakers, Shlomo Leibtag, and our guest speaker, Jack Saad. Shlomo is a research and development scientist at Industrial Sonomechanics. He's responsible for driving ISM's internal research. He graduated from Cooper Union with a bachelor's and master's degree in chemical engineering, and has published multiple journal articles on the formulation of nanoemulsion and optimizing nanoemulsion process parameters. Jack is an associate scientist with the scientific support group at Micromeritics Instrument Corporation. He's also the technical training and support manager. Jack has earned his bachelor's degree in chemistry from University of Georgia, and most of his early career was spent in pharmaceutical quality control. He joined Micromeritics in 2011 as a particle size application specialist. Here's also a quick overview of today's webinar. We will go over the ultrasonic nano-emulsification process by using BARBELL horn ultrasonic technology, which is Industrial Sonomechanics patented technology. We will then discuss droplet size analysis techniques and demonstrate how accurate droplet size determination is essential when high-quality nanoemulsions are manufactured. Now I'm going to pass the mic to Shlomo. Enjoy the presentation.
Thank you, Eva, for that introduction. So to begin this webinar, I want to start briefly on a discussion on nanoemulsions and how we formulate them and how we prepare them with BARBELL horn ultrasonic technology. So, nanoemulsions. Emulsions, you've likely seen them if you had cereal this morning, coffee, tea. If you've already been on your first beer, it's very likely you've encountered an emulsion already. An emulsion itself is a suspension of two immiscible liquids, one suspended as droplets in the other. And the droplet surface are mediated by surface active agents known as surfactants or emulsifiers. Now, nanoemulsions, there is a distinction between them from emulsions in that they exhibit long-term kinetic stability, which allows them to last in its dispersed phase for much longer periods of time, on the order of years or even longer. And generally, the droplets, the dispersed phase droplets, are below 200 nanometers in diameter. Two very common nanoemulsions that we all may have encountered today are tea and coffee. And the graphs shown here are particle size distributions. And the D50, or the median diameter of the droplets in these two products, are 25 and 82 nanometers for the tea and coffee, respectively. Now, it should be noted that there are different types of nanoemulsions. Nanoemulsions can exist both as water and oil nanoemulsions and oil and water nanoemulsions. The latter is much more common, and the difference between the two is which phase is dispersed. In water and oil nanoemulsions, water is dispersed within an oil, and in oil and water, it's the opposite, where oil is dispersed as droplets in water. On the left is an example of actually a water in diesel nanomulsion that was researched as a potential alternative and cleaner fuel. And on the right is actually a oil and water nanomulsion where a hydrophobic biopolymer was made into a nanomulsion, and then dried fruits were dipped into this nanomulsion to coat them and preserve their shelf life. So it's just here to demonstrate that there are different types of nanomulsions and they're used across many, many different industries. Our main concern with nanomulsions are oil and water nanomulsions, and that's because they allow you to incorporate hydrophobic bioactives into aqueous delivery vehicles. They've also been referred to as water-soluble oils. It's strictly speaking, the oils do not become water-soluble, but for all intents and purposes, in terms of mixing into water, they are. And we are interested in them because it can increase what's called the bioavailability of the drug substance or the oil that is suspended or that it's nano-emulsified. Simply put, bioavailability is the fraction of a dose that reaches the bloodstream as an intact drug. But generally, it is difficult to precisely measure how much of a drug gets you ingest and then how much actually gets to your bloodstream. So what is normally performed are called bioavailability studies is where a drug substance is administered intravenously and the same amount of that drug is given as some oral dose. And this can be done on humans or animals. And what happens is blood is drawn from the subjects over a period of time, and the concentration of the drug is measured, and you're able to build these curves. So for the IV dose, since that's going right into your bloodstream, that's considered absolute bioavailability, so all of the drug getting into your bloodstream, and some fraction of that gets into your bloodstream via an oral dose. And that's referred to as the absolute bioavailability, the ratios of the areas under these curves. Generally speaking, though, and what's often more reported in literature are relative bioavailabilities, where we will compare two different oral formulations. For instance, a drug substance in a tablet and a drug substance in a nano-emulsion. And what we can, by measuring the ratios of their respective areas under their curves, we can report an increase in bioavailability due to the delivery vehicle. A couple of demonstrations of this, of increased relative bioavailability, are shown here. For two supplements, on the left is bakelin, on the right is curcumin. And these are two bioavailability studies performed where the drug itself was delivered as just the drug or the nascent drug, and it's compared to the drug nano-emulsified. And what's shown here is that depending on the drug type and the nano-emulsion type, the increase in bioavailability compared to the nascent drug itself can be anywhere between 4 and 10 times. Remember, these are relative bioavailabilities, so we're comparing two different oral deliveries. And the motivation as to why nano-emulsification increases the bioavailability is an increase in surface area, or rather surface area per amount of drug as you make droplets. So that's demonstrated here in this study as what we see here are there's cyclosporin nano-emulsions. And as we're going upwards, we are decreasing our particle size. So down here, it's about 400 nanometer particles. Up here, 25 nanometer particles. And we see as we're going up, the area under these curves is increasing. So as we're making smaller and smaller droplets, more of the drug is getting into our bloodstream upon oral administration. And if we then take these values for areas under each of these curves and plot it versus their particle size, we're seeing that as our particle size decreases, our multiplier in bioavailability increase rises, and demonstrating how the reduction in droplet size and increase in surface area promotes an increase in bioavailability. It is important to stress that the components of a nano-emulsion should be carefully selected to make very fine and good nano-emulsions. So let's look a little deeper into that. The main nano-emulsion components, as we mentioned, consists of a dispersed phase and a continuous phase. For an oil and water nano-emulsion, water is the continuous phase, and some hydrophobic species and carrier oil drug substance is in the dispersed phase. And we take a zoom in on the droplet itself. Inside the droplet, there's usually a carrier oil, denoted in red, and there's a drug substance that's shown in yellow, but it should be noted that it's just shown in yellow. It's not that it's dispersed within the carrier oil. Rather, this dispersed phase is one continuous phase. The oil, the hydrophobic substance is all throughout it. It's just shown as droplets for pictorial representation. But it's important to drive home that inside that dispersed phase, there's both the carrier oil and hydrophobic bioactive. And then on the surface of these droplets are the surfactants, or the surface active agents. They preferentially adsorb to the surface. They have a hydrophilic portion, or a head, that associates themselves into the water phase. And they have a hydrophobic portion, or a tail, that actually goes into the dispersed phase. Now, when you do carefully select and optimize your nanoemulsion formulations, and you have the proper nano-emulsification technique, such as high-intensity ultrasound, you're able to make something called translucent nanoemulsions. Now, translucent nanoemulsions are nanoemulsions that have all their droplets well below 100 nanometers. And at that point, when light passes through them, instead of scattering, it actually goes right through. So you're able to see through them to some extent, get clarity. A couple examples are shown here, or a few rather. We have a soybean oil in water nanoemulsion, lycopene extract in water nanoemulsion. Lycopene is the red substance in tomatoes and other fruits, and we'll touch upon that a little bit later as well. And we also have a CBD isolate in water nanoemulsion that was made with nanostabilizer. And the same thing is shown for all these samples. As we're decreasing our particle size to the right for the soybean oil nanoemulsion, to the left for the lycopene extract nanoemulsion, and then back towards the right for the CBD isolate and water nanoemulsions, the droplet size is getting smaller, and the translucency, or the clarity, is getting better as for the you can start to see behind the samples. It's important again to drive home that all these nanoemulsions were both formulated properly and optimized, and all processed via high intensity ultrasound. Now, another benefit of translucent nanoemulsions when it comes to making finished products is that when you dilute them into a larger amount of water, so in this instance, we're diluting a 20 milligram CBD per mil nanoemulsion into a glass of water, and we're going to give it a quick stir. And upon that stir, the substance is clear. You can't see that any nanoemulsion is it. So for products that need to preserve optical clarity, translucent nanoemulsions are the way to go for that. So as mentioned, the formulation is essential, and so is the preparation technique. And BARBELL HORNO ultrasonic technology has been demonstrated to prepare very fine and translucent nanoemulsions at any scale. The basic setup of an ultrasonic liquid processor that utilizes BARBELL HORNO ultrasonic technology has a generator that's a power source that supplies the power to the water-cooled transducer. The transducer is water-cooled to allow for potential 24/7 operation. The transducer itself is coupled to a barbell horn, which delivers high amplitudes and subsequently high intensity cavitation, which we'll show in just a second. And that's inside of a reactor chamber that allows for high volume and continuous processes. So if we quickly just zoom into what is occurring inside the reactor chamber, the barbell horn is vibrating at high amplitudes and promoting high intensity cavitation to prepare, say, a nanoemulsion. And if we zoom in a little further, microbubbles or vacuum inside the liquid are growing and growing and growing until they eventually collapse on themselves and create high intensity shear that helps break up oil droplets to form very fine nanoemulsions. It should be stressed here that it's essential to have high amplitude to drive high intensity ultrasound. That being said, high intensity ultrasound has been achieved for a very long time on the small scale. By conventional ultrasonic technology, you can deliver high amplitudes to nanoemulsion samples, say of about 50 mils, and you can make really, really fine, good nanoemulsions that are translucent potentially. However, when you try to scale up conventional ultrasonic technology, say to about 50 liters, you need to make larger horns accordingly for the larger volume that you'll be processing. However, when you do that, by conventional horn ultrasonic technology, you can't achieve the same amplitudes anymore. So when you're going from your lab, your 50 mil experiment, to your 50-liter commercial batch, you're not maintaining the same ultrasonic amplitudes, and you're not maintaining the same quality of nano-emulsions. However, if you utilize BARBELL horn ultrasonic technology, you can make larger horns, so horns with a larger surface area to deliver a high-intensity ultrasound to great volumes, and you can maintain those same amplitudes. So when you do scale up, you're getting the same parameters that you set on your lab scale experiments. So now my session for the description of nanoemulsions is complete. And before we touch upon analyzing nanoemulsions by particle size analysis, I'm going to throw this back to Eva for a few questions from the audience.
Thank you, Shlomo. So we'll begin by having a couple of questions from the audience answered. As a reminder, if you have any questions to the presenters, please type them in the Q&A box, not the chat. The Q&A box is at the bottom of the Zoom screen. I'm also going to launch a few polling questions, which is a great way for you to participate in the webinar and also tell us what you would like us to focus on during the Q&As as well as in our future webinars. So you should see a polling question pop up on your screen now. So to participate, just select your answer and click submit. While we're doing that, I will have one of the questions to Shlomo from the audience. The first question is, how much carrier oil to cannabis oil do you propose for a good, stable nanoemulsion?
That's a good question. Ultimately, it will depend on which carrier oil you're using, but we see generally about 2 to 1 will work. Carrier oil to your extract or isolate. That's a reasonable place to start, but it'd be good to study that if you are preparing nanoemulsions, and we'll actually get into some carrier oil studies we performed a little bit later.
Another question we have is, do I need to use a surfactant to make my nanoemulsion? Can I just mix my active ingredient with water and sonicate to make the nanoemulsion?
So generally you will need some amount of surfactant. If you select the right surfactants and you have the proper nano-emulsification technique, you could limit the amount of surfactant, but you always need some. But part of the optimization protocol can be minimizing the amount you use.
All right. Now I'm going to go ahead and close the polling question and that, and we'll continue with the next section of the webinar, which is Jack's section on particle size analysis of nanoemulsions.
Well, thank you, Eva. Hello, my name is Jack Saad. I'm with Micromeritics Instrument Corporation. And again, I'll be talking about particle size analysis of nanoemulsions, particularly focusing more on the techniques and how we actually characterize them. Let's see if this cooperates. There we go. So the common techniques that we use, one is called laser diffraction. This is primarily in the micron range, but you can get down into the nano range. Other names for this technique are static light scattering, or Fraunhofer diffraction, or Mie scattering. The typical size range for this technique is 100 nanometers to about 1 millimeter. Different brands, different engineering of instruments, they can extend that range a little bit depending on, like I said, how it's made and the detection system, the laser, the light source, things like that. You can probably get down to 10 to 40 nanometers, as high as 2.5 to 3 millimeters. But the typical range, like I said, is 100 nanometers to 1 millimeter. For nanoemulsions, they're primarily used for emulsions that are just above 500 nanometers. So greater than or equal to 500 nanometers, laser diffraction works well. It's good for wide size distributions, especially when you have an unknown material or unknown sample, where you're not really sure where your sizes are going to be. And, it could be, up in the micron region, like 1 to 2 microns, or it could be down as low as just under 500 nanometers. But if you're just not sure, then it's a good technique to use to kind of get an idea of where you're standing. The other technique I'm going to discuss is dynamic light scattering. Dynamic light scattering is a nanosizing technique. It also uses light scattering. Other terms or names for this technique are photon correlation spectroscopy or quasi-elastic light scattering. The typical range for this technique is just under 10 nanometers up to about 10 microns. It's primarily used for emulsions less than 500 nanometers. Again, also I mentioned the range 10 nanometers to 10 microns, just like laser diffraction, depending on the engineering of the instrument and the detection system, light source and things like that. You can probably get a little bit lower. I'm not too sure about getting a little bit higher than 10 microns, but I'll explain that in a few minutes. This technique is really good for narrow size distributions, especially in the nano range, less than 500 nanometers, more like, less than micron really, but less than 500 nanometers down to all the way about a few nanometers. And it's nice for if you have an expected size. So if you've measured something with laser diffraction and figured out where your emulsion is, you can use dynamic light scattering to kind of fine tune it. So going back to laser diffraction, we use me theory to make this measurement. You can see how particles of certain sizes will interact with light in different ways. The most common way is diffraction, which is usually for larger particles greater than 50 microns. Once it starts to get smaller, you get a lot of refracted light, where you need to take into account the refractive index of the material and the absorbency or transparency of the material. And that will affect, or you'll use me theory to make that calculation. And the way me theory works is that you're looking for small particles that are going to scatter light in large angles, which is, like I said, diffraction, or large particles are going to scatter light in very small angles. I'm sorry, that one's diffraction. Small particles scattering light at very large angles, that's how we're going to be measuring the nano-emulsions. So in this graphic, you can see how laser diffraction works. You have a light source, it interacts with the cell that's containing the emulsion, and the scattered light is collected by a lens and focused onto a detector. Now, different instruments kind of operate in different ways. In this particular case, this instrument by Micromeritics can vary the angle, and you can see how the angles will affect the data collected, and we take that into account in different algorithms, and we're able to calculate a particle size distribution. This is done by looking at the angle and the intensity of light at each one of those scattering functions. And each one of those scattering functions, the little I of theta, we can use those to calculate a radius. And when we calculate a radius, we double it to get a diameter. And when you take into account the entire array of different angles and the different intensities, you get a distribution of sizes. Here's an example of some size data where I mixed different size latex materials. These are latex microspheres, 1 micron, 1.6 micron, 2 micron, 3 microns, all the way up to 10 microns. And I mixed them all together, and you can see how you get a size distribution in one analysis. And you can also get additionally more specific results or specific data like mean, median, and mode of the entire distribution, as well as statistics on the individual peaks and the individual sizes. Here you can see where the mean is, pretty much where those reference materials that were purchased from Thermo Fisher, how much they agree with the actual label claim. So this is the typical data, again, that's reported by laser diffraction. With dynamic light scattering, we're looking at the emulsion suspended in a cuvette, and we're looking for Brownian motion. Now the particles are so small, they're not settling out, and they're not moving around, or they're not moving in any kind of motion. The suspension is held stationary. And we're looking at looking for Brownian motion. Brownian motion is when the particles or the molecules of the liquid are colliding with the particles or the emulsion, and causing them to move around at a certain rate. This movement is random. However, the rate of their movement is, we can find some correlation. And the idea is we're looking at the light, how it scatters and how it's fluctuating over time periods. So the idea is that small particles are moving fast in Brownian motion because of their relative size to the water molecules or liquid molecule. And that's going to cause a rapid scattering fluctuation. If the particles are large or larger, relatively speaking, the Brownian motion tends to be slower and you get a more moderate fluctuation. So this is how we can kind of correlate the scattering fluctuation back to a size. So we're looking at the scatter light again and looking at that fluctuation over a time period, and we're looking at the intensity, and we're focusing more on the distance between these peaks and valleys. If they're really close to each other in time, that's a rapid fluctuation. You tend to have small particle sizes. If you see a much broader distance between the peaks and valleys over a time period, it's a more moderate fluctuation, and you have larger particle sizes. So we put all that together into this autocorrelation function where we're looking at overlaying the scattering fluctuation data, and we overlay it of different time periods, and we look for a decay curve called the autocorrelation function. And in this function, you'll have a graph where it basically starts to decay. The y-intercept here is the b in this calculation. The point where it starts to drop, that's where the size is going to be located, or where you're going to calculate the size from. This slope of this line of this decay is the polydispersity index. And then when it goes all the way down to flat, to baseline, that's where there's no correlation. So here you have high correlation at the top and no correlation, and you have this gradual decline to baseline over a time period. And this is again G2 of tau, which is tau is the time delay, which is that overlapping time intervals, and we're looking for that correlation. We're using all of this to calculate the diffusion coefficient, which is this capital D, from the decay constant. Once we have that diffusion coefficient, we can use the Stokes-Einstein equation. We know the Boltzmann constant, we know the absolute temperature, we know the viscosity of the suspending liquid. We can calculate a hydrodynamic diameter. Notice in the previous slide, I underlined the refractive index of the liquid, and here I have the viscosity of the liquid. These are the primary liquid that's suspending the particles. So it's you have to know these properties in order to make this calculation work to generate an accurate size. Also notice that I'm calling this the hydrodynamic diameter, not the actual diameter. And the reason is that this is because this is the diameter of the size of the particle based on its movement in water, which is the Brownian motion. So when we're reporting size data from DLS, there's a number of ways to report the data. The most accepted way for reporting size data is based on the ISO 22412 method. Its last revision was in 2017. It basically describes the cumulance average, or Z average, and the polydispersity index as the primary data you report. The Z average is reported in nanometers, and the polydispersity index is unitless. Polydispersity just tells you how broad the distribution is. It's usually a value between 0.01 or 0.001 up to about 0.7. Anything above 0.7 for polydispersity tends to be too broad for dynamic light scattering to really work well. Since this is an intensity weighted measurement, the primary distribution data is reported in terms of an intensity weighted distribution. You can also calculate a volume and a number weighted distribution from the intensity weighted distribution. However, there's like some additional assumptions that are made and how this data is calculated. Another thing to look at is how the distribution results are calculated. They're commonly used by the content method or non-negative least squares. There's other less commonly known algorithms used to calculate distribution data from the autocorrelation function. But like I said, content and non-negative least squares are the most common. And with that, that concludes the characterization portion. I'll hand it back over to Eva to check for any questions that may have come up.
Thanks, Jack. So there's a question from the audience. It looks like there is an overlap in the size range around 100 nanometers to 500 nanometers between laser diffraction and dynamic light scattering. Does it really make a difference which instrument we use?
Yes, it does. Actually, I'd say yes and no. The reason there's an overlap is that, well, of course there's gonna be an overlap, but going back to the physics and of the instruments and the techniques and the engineering of the instruments, they typically use red lasers. Red lasers are about 630 to 660, 670 nanometers in a wavelength. So when we're looking at particle sizes that are less than 500 nanometers, we can use laser diffraction. However, me theory starts to kind of not work so well because you're getting smaller than the wavelength of the light. And when you're getting smaller than the wavelength of the light, you're getting away from me scattering, and the particles are scattering light as Rayleigh scattering. And Rayleigh scattering is one of the operating principles of the of dynamic light scattering. You're assuming that the light is scattered in all directions equally by the particles. So there is going to be an overlap. However, when you starts to get into those lower limits of laser diffraction, you'll start to lose resolution. You won't be able to pick out size peaks as easily as I showed you in the polymer sample for laser diffraction. At the same time, for dynamic light scattering, as you start increasing in size, you start to have gravity, which is competing with Brownian motion, pulling on the particles. So you have sedimentation as well as Brownian motion. So when you start getting to the limits of dynamic light scattering on the higher end, it's also the operating principle starts to kind of fall apart a little bit, and the data may not be very well repeatable. So it's, I would say, like I said earlier, that with laser diffraction, it's good for unknown samples. It gives you an idea of where it's at and shows trends. Dynamic light scattering is more for fine tuning it, because again, we're starting out with something that's going to be pretty large and then working our way down to getting it to a nano emulsion. So using the combination of the two is good. If you have one or the other, you just have to be aware of the limitations of the technique and of what it's actually measuring.
So if you have a translucent nanoemulsion, which is below 100 nanometers, the dynamic light scattering would be more appropriate as a measuring technique.
Yes, yeah, it's more appropriate because again, you know, as the nanoemulsion gets smaller and smaller in size, it interacts with light less and less. You'll still have Brownian motion, the particles will be moving around, and you'll still see scattering fluctuation. But again, when you start looking at me scattering, which is how laser diffraction works, you're not going to be able to see it very well. So yeah, definitely laser or dynamic light scattering is the appropriate technique with translucent nano emulsions less than 100 nanometers.
All right, so let's pass the presentation back to Shlomo and finish up with the last section for the formulation and optimization of nanoemulsions.
Righty. Thank you, Jack and Eva, and everyone for participating thus far. So when I started, we discussed nanoemulsions, how we formulate them, preparation techniques, and we went into how we analyze them by either laser diffraction or dynamic light scattering. And now I want to try to bring those together and show how we can utilize the particle size analysis to optimize formulation techniques and nano-emulsification processing parameters. So in that, we want to, I'm saying, gain insight into nanoemulsions, how they're formulated, and nano-emulsification. And to do that, we'll focus on two research objectives. One was the formulation of a CBD extract nanoemulsion, not made with nanostabilizers. It was made with nanostabilizer. It was made with some generic surfactants known as Tween 80, Spain 80, and we'll look into how the use of carrier oils and the HLB of the surfactant system can help you optimize or minimize the droplet size. And then we'll get into processing parameters. For a lycopene extract nanoemulsion, Again, lycopene is the chemical or the hydrophobic species in tomatoes and other red fruits and vegetables that give it its red character. And we'll look into how nanoemulsions of these type exposed at different ultrasonic amplitudes and processing temperatures affect what's called the processing rate or the productivity, or in the simplest terms, how much nanoemulsion can I make in a given period of time. So we'll start with our CBD extract nanoemulsions. And the first thing I want to touch about is the importance of carrier oils. So anyone who's familiar with cannabis extracts or other extracts of that nature, they're thick and they're difficult to handle. So by incorporating a carrier oil, you can more easily dispense them, get them into your formulation tank. So that's one advantage. Additionally, triglycerides or fats that are common carrier oils possess essential fatty acids that help with the absorption of hydrophobic bioactives. And lastly, among other items, carrier oils can help limit what's called oswald ripening, which is the primary destabilization mode for nanoemulsions. And it's a process in which small droplets in a nanoemulsion eliminate and deposit onto larger droplets, which then have enough buoyant forces to raise, flocculate, and eventually cream and coalesce. So it's clear that carrier oils are important, they're essential. However, it would make sense that as we're increasing the amount of oil in our nanoemulsion system, we are creating more and more surface for the surfactants to coat. And if we're keeping a constant amount of surfactants, we would expect that as we increase our carrier oil concentration, we're going to see an increase in particle size. So we wanted to look into this for a CBD extract in water nanoemulsion. The nanoemulsions here contained 5.4% CBD extract, 4.5% saponin content from Q Naturel, which is a possibly organic surfactant. And we modulated carrier oil, olive oil in this case, from 0 to 14%. So we were able to make this curve where we actually observed that initially when we increase our carrier oil content, so from about 0 to 4% olive oil, the droplet size actually reduced. And then when we got to above 10% or so, the droplet size increased. So this mode over here we predicted, but this was unexpected. And the reason we justify this, or the reason we think this is happening, is because we are reducing the viscosity of the dispersed phase. And now viscosity, by definition, is the resistance to shear. So if we decrease our viscosity, then we're more acceptable to the shear forces that we're preparing these nanoemulsions with. Again, we did see an area where these effects counterbalanced. And then again, above 10%, the oil loading is overwhelming. So what we made as an optimum was the midpoint of this plateau where the effects were counterbalancing each other. And that corresponded to an optimum nanoemulsion with 5.4% cannabis extract, 7.2% olive oil, and 4.5% saponin content. Now, the next mode of optimization involved utilizing a surfactant system. So, as mentioned before, surfactants contain both hydrophilic and hydrophobic portions. And we are zooming in on the schematic of an nanoemulsion droplet. And our sample surfactant in this case will be tween 80, which consists of a hydrophilic portion with many ethoxylate groups that can participate in hydrogen bonding and want to be in the water phase. And they have a hydrophobic portion, in this case, which is oleic acid, which associates itself into the oil phase. Now, this balance between hydrophilic and hydrophobic portion of the surfactant is known as the hydrophilic lipophilic balance, or the HLB. It's a property of the surfactant. Now, the oil phase itself will have a required or optimal HLB in which it achieves a minimum droplet size. So various surfactants have different HLBs, And you could you could go through several different surfactants to test out HLBs, but you end up having to test several different surfactants. And it's actually simpler to just take two surfactants and perform an optimization like this, where you take two surfactants and you can modulate the HLB of the system by maintaining a constant surfactant amount, but changing the ratios of one surfactant to the other. So for the studies that we were about to describe, we took tween 80 and span 80, and we kept their total content the same, but modulated their mass ratios, and we were able to change the HLB from 4.3 to 15 like that with just two surfactants to determine where would the optimal HLB be for the for this cannabis CBD extract. So we performed this study on two different nano-emulsions, one with just 5.4% CBD extract and 4.5% total surfactant of either tween 80 or span 80, and another nano-emulsion which contained the optimum amount of carrier oil that we determined in our previous study, also with 4.5% total surfactant. What we see off the bat is that just changing the HLB can greatly help minimize your droplet size. And that optimum droplet size was about 13, or rather that optimum HLB was about 13 for both nano-emulsions. What we saw again here was that the presence of a carrier oil greatly reduced the droplet size. So where the optimums, both of them are 13 HLB, but at that optimum, the droplet size for the just CBD extract was near 500 nanometers, and the optimum, the droplet size for the nano-emulsion with olive oil at the optimized amount was near about 140. So even though you're doubling the amount of total oil, you're reducing the droplet size by almost 4 times, about 4 times. So we took that optimum HLB, and we took the optimum carrier oil and CBD extract content, and we performed a translucency approach with the this tween 80 span 80 nano-emulsion and the optimized Q natural nano-emulsion that we described previously with the carrier oil study. And we just increased the surfactant amount. This value here is known as phi, and it's the ratio of total surfactant to total oil. So as we're going from left to right, we are increasing surfactant until we approach about 1, so a 1-to-1 ratio of both total surfactant to total oil. And for the Q natural nano-emulsion, which you see in the blue line, we reach about 110 nanometers or so, and then the effect plateaus, and we actually don't reach translucency. So in this picture here, you can't see it, but there's a laser light being shined from behind the sample, and you can see it faintly over here, but it's definitely not coming through the sample. Now, for the tween 80 and span 80 nano-emulsion, as we maintain the same HLB, yet just increase the total surfactant amount, we actually are able to achieve translucency, where you're able to see the light pass through the sample rather strongly. The optimized translucent nano-emulsion came out to be about 5.4% CBD extract, 7.2% olive oil, 10.4% tween 80, and 2.2% span 80. So all these studies were performed on all the studies we've described until now were performed on a lab scale sonicator, and we utilized laser diffraction to measure the droplet size. At this point though, now that we knew our droplets were translucent and below 100 nanometers, we moved our analysis approach over to DLS, and we wanted to demonstrate that this process could be scaled up to potential commercial volumes. So what we did is we took this optimized translucent nano-emulsion, and we performed a scaled up nano-emulsification demonstration with dynamic light scattering. So in this setup here, we have the BSP 1200, a bench scale ultrasonic liquid processor in which this study was performed. All of the contents of the formulation were placed into the tank. They were mixed, and they were then pumped around into the ultrasonic reactor chamber and then back into the tank and recirculated likewise. And over time, at selected times rather, we pulled samples and measured the droplet size. And we can see that the decreasing droplet size again correlates with an increase in translucency. These again are pictures of a light being shined from behind the samples. And the processing time, or rather, the processing time in which the droplet size plateaus, essentially where our nano-emulsification was complete was about 40 to 60 minutes. And that corresponds to 5 kilograms of total nanoemulsion per hour. That includes water and all the contents. And at the concentration that these studies were performed, that corresponds to nearly or just above 1 million 10 milligram CBD extract doses per month with just a single BSP 1200. So this demonstrates that this process of nanoemulsification is scalable and could be brought to a commercial application. So before we finish up our webinar today, I just wanted to touch upon processing parameters and how we can optimize them with particle size analysis. So the two parameters that we're interested in now are the effect of ultrasonic amplitude and processing temperature. So as we mentioned earlier, high amplitudes and consequently high intensity ultrasound are essential to making very fine nanoemulsions. However, we want a tangible way to compare how conventional ultrasonic technology would compare to BARBELL HORNO ultrasonic technology. So we did several studies where we performed the nanoemulsification at low amplitude to correspond to the maximum achievable amplitude by conventional ultrasound at scale. And we did studies, or we projected studies at the maximum achievable amplitude by BARBELL HORNO ultrasonic technology. And we compared the processing rate between these two, or the productivity, or how much nanoemulsion can I make in a given period of time. The second parameter of interest was processing temperature. Processing temperature is a real important parameter in almost all chemical or biochemical processes. However, it's not particularly studied in regards to nanoemulsification. So we wanted to look into that a little bit. And we suppose that there could be two types of behaviors with temperature and nanoemulsification. So in these supposed graphs here, we have droplet diameter decreasing with increasing processing time, nanoemulsification processing time. And in type 1, the processing rate is faster. We get down to smaller droplets more quickly at higher temperatures than at lower temperatures, but ultimately with enough time, we get to the same place. So that's our type 1 possibility. And type 2 would be that at higher temperatures, we get an increased processing rate and we're able to achieve smaller droplets. So these are two modes of how processing temperature could affect nanoemulsification. And we looked into this with the lycopene extract and coconut oil in water nanoemulsions with tween 80. And in the studies performed here, we operated at 4 different temperatures. And we can see that at the highest temperature, the processing rate is both the fastest. We get down most quickly in the shortest amount of time. And we're actually able to achieve the smallest droplet size. So with increasing temperature, our processing rate increases, as also our droplet size decreases for this nanoemulsion formulation. We performed this same study at a nominal ultrasonic amplitude comparable to the maximum that conventional ultrasound can achieve. And we performed the study at 2 times that amplitude, which comes out to about 70% of the maximum amplitude with BARBELL HORNO ultrasonic technology. So that's the red line. And then the dotted green line is projected what the maximum achievable amplitude with BHUT would be. And again, for all amplitudes, we're seeing that as we're increasing our processing temperature, our processing rate is going up, which makes sense. And as we are increasing our amplitudes across each line, our amplitude is increasing, almost doubling about doubling when we double the amplitude from the green to the red line. And that's important in and of itself, but as a further matter, for compounds like lycopene, shown here, which can be susceptible to isomerization and other degradation with temperature, if you can operate at high amplitudes, you can still maintain high processing rates and not exceedingly high temperatures. So with conventional ultrasonic HORNO technology, you would have to go above 55 C to actually achieve a processing rate that can be easily achieved below 40 C at a nominal amplitude, and even higher with what's achievable with BARBELL HORNO ultrasonic technology. So that's what's demonstrated here. And that completes our discussion on how we're utilizing, or how we've utilized particle size analysis to optimize formulations and optimize processing parameters. And it completes our webinar for today. And I thank you all for listening, and we're glad to take some more questions and supply some answers for you guys.
All right, let's go ahead and answer some of the audience questions. If you have any additional questions, please type them in the Q&A box. So the first question I have is, how does ultrasound mixer compares with high shear mixers?
Yes, so ultrasound is actually providing high intensity mixing. A high shear mixer can't provide the same intensity that you're able to provide with high intensity ultrasound, so you won't make very fine droplets. So if you can ever form the very small droplets, then you can't sustain them. So it doesn't matter how good your formulation is. If you don't have the proper technique to make fine droplets, which high intensity ultrasound can provide, then you'll never make small droplets. So that's the essence of why both the formulation and the method of emulsification are essential and tied really together.
Before we continue with the next audience question, I'm going to launch another polling question for the audience to participate. Here you go. It should pop up on your screen right now. And you'll have a couple of minutes to participate by answering those questions and submitting them. Meanwhile, the next question that I have for Shlomo is, can you make translucent solution at 50 milligrams per milliliter CBD using distilled CBD?
Yeah, you can. You will just need the proper formulation. So that it is achievable with nanostabilizer, which is Sonomechanics formulation that was optimized for CBD extracts. It is achievable with those. With other formulations, it may be possible, but those would have to be on a case-by-case basis. But certainly with nanostabilizer, it is.
Great. I also have another question for Jack. Does dilution factor has impact on particle size? How can you be sure? And how can you find the best dilution factor to determine the size of droplets by dynamic light scattering?
That's basically, you have to, the standard procedure for something like that is to just make dilutions of the suspension and continue to make dilutions and make measurements. So you dilute it like, by known amounts, and the liquid you're using to make the dilution has to be identical to the liquid that is, holding the suspension originally, without the oil or without the suspension, without the particles. So that way, if there's any like salts, or if there's any kind of ions or pH or anything like that, all that has to be included. So you're making the dilution without affecting the chemistry of the suspension, and you're monitoring the changes in size. If the size does not change, then you have an optimal dilution or an optimal concentration. If it does start to change, you want to continue diluting until you see no more changes. Or if it starts to increase in size, then you start to see, where your main particle size is. It's basically just trial and error and creating a method where how are you going to prepare your sample, and how are you going to use the nano emulsion itself. If you're going to use it in a concentrated form, maybe the particle size itself, the specific particle size, may not be that important. Maybe the trend on how conditions may affect it. If you're, adding it to another ingredient or another process, what's going to affect it. So looking for trends in the concentrated size might be more beneficial in investigating. But if you're looking for the absolute particle size, just making serial dilutions with the base liquid and monitoring the size and looking for a point where the dilution, no matter how many more times you dilute, it's not changing in size.
Thank you, Jack. The next question is for Shlomo. How does a finished nano-emulsion not dispersed in water stand up to heat?
Not dispersed in water?
Yes.
So, well, that will ultimately depend on what the continuous phase is. If the continuous phase can survive the temperature that we're supposing here, then the emulsion should stay intact. If we're getting some evaporation of the continuous phase, it may survive for a certain period of time, but there will be a breaking point where you'll lose too much of your continuous phase, and you may destabilize your nanoemulsion.
Thank you, Shlomo. I have another question for Jack. What is the relationship between electrostatic repulsion, charge separation as measured by zeta potential, and static repulsion? Specifically, does the bonding of polymeric surfactants required for static repulsion, and does it affect zeta potential?
Is steric repulsion you're talking about, or?
Steric repulsion.
Steric repulsion. Yeah. So steric repulsion is probably going to still be the best way to keep particles or emulsions separated from each other. With zeta potential, it's important to keep those values in mind. Zeta potential is actually a characteristic of an entire suspension. So it includes whatever's in the liquid, whatever's in the continuous phase, whatever's in the emulsion, whatever's suspended in the emulsion, if it's like some kind of drug or like a pharmaceutical application. Zeta potential is a characteristic of the total suspension. So anything changes, like a small change in pH, you might change the zeta potential. It's more of even though it's a quantitative value, you actually get a number. It's still kind of a qualitative result because it's of the suspension, not of the particles themselves. So even though you may have small changes in zeta potential, the suspension may still be stable due to steric repulsion. So I would say for something like that, just keep the zeta potential in mind, documented for information purposes. If you see dramatic changes in zeta potential, then you can investigate, what's going on. Maybe one of the components that was added or something may be different, or something else is going on. But for the most part, either or. People like zeta potential because it doesn't, especially for something like, medications and stuff that you drink, it doesn't give it a syrupy taste. When you have, because the zeta potential, when you stabilize it with zeta potential, it's like a soda or coffee or something like that, where it's, stabilized and suspended and it's not separating, and it flows like water. The more that it flows like water, the easier it is to drink.
One more question for Shlomo. Particle size is very helpful to know. However, I wonder how we can confirm the concentration in milligrams per milliliter post-filtration. Does the large particles get held in the filter, and does it alter the final concentration?
Got it. Okay, so there's a couple questions there. In terms of content analysis for nanoemulsions, they can be performed. You can use HPLC, but liquid chromatography, UV vis can also be utilized, and we do it in-house to measure the content of nanoemulsions. The point about filtering is key. So if you're making an emulsion, and even if your average droplet size or your median droplet size is 100 nanometers, and you try to sterile filter that with the 220 nanometers, you will still lose some droplets because, as we've seen before, it's a distribution. So you could have a medium particle size, but you still have plenty that are above that. So if you do filter an emulsion that is much larger, or if it has any larger particles than the pore size of the filter, you will lose concentration. They can't get through. That's why it's very important to know your particle size, and why translucency is key, because that ensures that your droplets are well below 100 nanometers. So I think that answers that.
Another question is, if you were to run a 2-to-1 nanoemulsifier to product or oil, active ingredient, I assume is what they mean, and decided you wanted to be more transparent, can you rerun the material through the ultrasonic processor with more nanoemulsifier to increase the ratio?
Yeah. Yeah, I mean, as long as you know what all, yeah, as long as you know the components in it, so you're sure that you were 2-to-1 before, and you had the proper amount to make it up to 5-to-1, then yeah, you should make a translucent nanoemulsion. For emulsions, maybe I think they're referring to nanostabilizer, right, Eva?
Yeah, I believe so.
Yeah. So for emulsions made with nanostabilizer, the order of insertion doesn't matter as much for the final value. It may take longer if you mix all things in a weird order, but eventually, if you provide enough ultrasound, you should achieve the particle size that is dictated by the ratio. So what I'm saying is that if at 5-to-1 you get to 20 nanometers, and you made a 2-to-1 that is at 150, and then you added 3 parts, you should get down. Or rather, 3 parts, you should get down to 20 nanometers.
And I think we have a little bit more time for a couple more questions. One of them is there anything unique with olive oil in your formulation? Will other oils work for making nanoemulsions?
Yeah, plenty of oils can be used as carrier oils. We just demonstrated olive oil for these studies. But for instance, in the lycopene studies, we used coconut oil as a carrier oil. Also in this, we showed their soybean oil nanoemulsions. So, basic triglycerides are great to emulsify. It's up to your choosing. Some work better for digestion purposes for absorption, but in terms of making the nanoemulsion, you could use almost any food oil that you would use for cooking or baking or salad dressings. Any of those oils could work.
And we have time for one more question. And does the nanostabilizer have any synthetic surfactants in it?
So synthetic, no. All the components in nanostabilizer are naturally derived. But you can't put a claim of natural on things if there's any sort of refining process for the components. So we don't. But all the components are generally regarded as safe or GRAS, and they've been used in plenty of other nanoemulsions for both food and beverage and pharmaceutical industry. So they're generally safe.
Thank you very much, Shlomo. And thank you, Jack. And thank you everyone for attending today's webinar. We hope to see you at our next event. If you guys want to get in touch with either Shlomo or Jack, you can do so at the email addresses that are on the current slide. Otherwise, if you have any additional questions as well, you can submit them either through our website or by emailing them directly. And that concludes today's webinar. Thank you again for participating and have a great rest of your day.